I have chosen to draw a chart out in advance for you this time on this video. Please note that when you have an equal to included in your inequality, the graph that you draw will be a solid line. But if the equal to is missing, then you will use a dotted or a dashed line. When you have a greater than or equal to, we shade above the inequality. Less than or equal to, we shade below. However, I put little asterisks here to remind you that the equation must be in slope-intercept form, or at least have the y isolated on the left side of the inequality. In this first problem, both of these are already in slope-intercept form. I notice that the first line has a y-intercept of 3, which I plotted, and a slope of -2. Notice I drew that as a dotted line because the equality was missing. But the second line, which had a y-intercept of -2 and a slope of rise 1, run 2, was a solid line because the equality was included in the inequality. Now, let's talk about the shading. Greater than means for this line with the negative slope, we will be shading above the line. However, for this other line, we will be shading below. Technically, there is an included "and" in this system where we want to shade the intersection of these two solution sets where they overlap, which gives us this triangular region down in the bottom right corner that has a solid boundary above it and a dashed boundary below it and to the side. This is the set of points x, y for which the inequality holds true. For example, I can go out here to 5, -1, which should be part of the solution set, and verify that 5, -1 works in each inequality. And I could also check that 0, 0, the origin, does not satisfy either of the inequalities. When you have vertical lines, you cannot shade above or below them. For this x less than 2, I can't shade below it, so in this case we will shade to the left of it. That's the only exception to the above-below rule. However, for this vertical line, we definitely can shade above it, and we notice that in the top left corner we find the intersection of these two shaded regions, and that is the solution set for this problem. Now, on this third inequality, we see that there is a less than in the problem. Do not jump straight into shading below a dashed line. First, we need to look at where will the x and y intercepts be. Now, I'm going to start by substituting 0 in for x. Pretty much that leaves -3y equals 15, so y equals -5, if this were a solid line, would be the y-intercept. If we let y be 0, we would have 5 times 3 is equal to 15, so 3 would be the x-intercept. So I will plot a couple of points at those locations, noting, however, that these are actually not points at all. These are not even in the solution set, but this will be a dashed line boundary. Now, if we had switched this to slope-intercept form, had we subtracted 5x, -5x plus 15 on the right, and then divided by -3, notice how that would have changed to a greater than inequality, because whenever we divide by a negative, we change the direction of the inequality. Now we can see that this is actually a greater than inequality in which we will be shading above. When your line is given to you in standard form, if you see a negative in front of your y coefficient, that is a clue that your inequality is going to be changing directions and that this would not be a shade below, but instead rather a shade above situation. Now, if you could read through this very quickly, basically they want us to write an inequality to show how he can get enough points for an A in the class. Now, it says at the top that he needs more than 60 points to get an A. So we know right off the bat we're going to have a greater than 60 in our inequality. Now how does he gain points? He gains 2 points for each question of type X and 4 points for each equation of type Y or problem of type Y, and pretty much that will be the inequality we're looking for, 2x plus 4y greater than 60.